Hi folks, it's Matt again. So what we're going to do now is look at a few examples that'll illustrate some of the notation and definitions you've seen in terms of mechanism design. So let's go through that. So let's look at a particular example. And this is going to be an example where there's a society of people making a decision over a candidate. So they're electing somebody. So we've got the N that we talked about is now a committee of voters. So we'll index them 1 through N, little n. And those are the maybe people in the legislature. They could be people in a town. They're people making a decision over a candidate. Here, the outcomes now are the candidates, so we'll label them A, B, C. So in this case, let's keep it simple. We'll have 3 candidates who could possibly be elected. In this example, what we're going to be looking at is one where there's private values. So the people involved have preferences where they know their own preferences. So the types that we looked at before, these theta i's, fully capture all of the preferences of the agent. So for instance, there might be some type of a particular agent, say theta tilde, which is one who likes candidate A the best, B second, and C third. And in this case, we'll keep things simple. 3 units of utility for A, 2 for B, and 1 for C. So that would be one possible utility. So then in terms of our notation, that means that the utility function here for I as a function of the outcome and theta tilde depends only on the person's own type, right? So it doesn't matter what other people's types are in terms of determining that utility. Okay, so in this particular example then, that means that ui of A and theta I is 3, B and theta I is 2, and C is 1. In this case, we should have subscripts on the U's. So this is a simple way of representing it. This is private values. That means that the person doesn't need to know the other person's types in order to figure out what their utility is. They know how they value the candidates, and there's no information out in the society that would change that. Okay, so what we'll do in this example is keep things very simple again. We'll have 3 possible types. So there's the theta tilde who likes A the best. There's another type, theta hat, who likes B the best. And a type theta bar who likes C the best. So in this case, theta tilde likes A, then B, then C. Theta hat likes B, then A, then C. And theta bar is a C, then A, then B. Okay? And we'll look now at what the implications of that are going to be for the voting. So in terms of probabilities, let's think of a world where most of the people are either tildes, the people who like A the best, hats, the people who like B the best, and there's a small percentage of the population who are people who like C. And we'll think of these as distributed independently across the society. So each person gets their own draw, and knowing your own type doesn't tell you anything about what the rest of the society looks like in this particular example. Okay, so now let's talk about what a mechanism looks like in this world in terms of the notation. So here, let's think of plurality voting, so a very common voting system. Each person just picks which candidate they'd like to vote for, and the rule picks the candidate named by the most agents. So this is probably one of the most simple and canonical of all voting mechanisms. And in this situation, our actions for each player, each agent in the society, is just a list of the candidates. So they can declare that they vote for A, B, or C. Then the mechanism takes those announcements that the people have made and makes a choice of outcomes, which could be random. And in particular, if, for instance, the votes were B, B, and C, then it would pick candidate B. That would be the person named by the most. If there's some tie, then it's going to randomize and it's going to pick among those getting the most votes. So for instance, if you had a society that split a third A, B's, and C's, then it would pick each candidate with probability 1/3. So that's the outcome function, which is mapping from the announcements of the agents into some distribution over outcomes. Okay, so now we've got our mechanisms and so forth. And so now we can talk a little bit about the solution of one of these. So what would happen? How are people going to behave in this society? So first of all, let's note that there aren't any dominant strategies to this mechanism. So to think about that, let's think of a world where we've got an odd number of voters, so we're not going to have to worry about people. That'll make our life easier in terms of ties. And let's think of a world where we've got at least 5 voters, and that'll become clear in a moment. So let's consider the type theta bar I. This is the person who likes C the best, and then A and then B. Okay, so what's that person's choice? Should they be always voting for C? Well, that's not completely obvious, right? So if half of the other voters voted for A and half of the other voters voted for B, then that's a situation where now they're going to be the decisive voter. If they vote for A wins. If they voted for B, then B would win. If they voted for C, then it would be a runoff. It would still be that A and B would be tied because there's at least 5 voters. So that means that there's at least 2 votes. So we've got at least 2 votes for A, at least 2 votes for B, and no votes for C. So that means that if this person votes for A wins. They vote for B wins. If they vote for C, it's going to be a coin flip between A and B. They prefer A over B, so they should vote for A, right? So then they're best off voting for A in this situation. In contrast, if you go through the same calculation, if half the other players voted for C and half voted for A, then you're better off voting for C. So what this tells us is that how this person votes actually depends on what they're thinking the other people in the society are going to do. So if they think the other people are splitting between A and B, they should be voting for A. If they think other people are voting for C and A, they're better off voting for C. So this means that there's not a dominant strategy in our standard sense in this kind of game. Okay. So when we start thinking about this, and actually just here that you can go through, here there wasn't any dominant strategy when we're in a situation where there was at least 5 people voting. If you go through the same kind of reasoning, think about what's the case with n equals 3. So that'll test your understanding of this. Think a little bit through how this person should be behaving in the case where there's actually just 3 voters. So there's many Bayes-Nash equilibria to this game. So in particular, for instance, everybody voting for candidate A is in equilibrium. Why is that in equilibrium? Because if everybody else is voting for candidate A, then regardless of what I do, there's going to be a majority of people for candidate A, so I might as well vote for candidate A. It really doesn't matter what I do. Similarly, everybody voting for candidate B is in equilibrium. So these will both be Nash equilibria. You're also going to have one where everybody votes for candidate C. Here I put that this isn't sensible. Why isn't this sensible? Well, it's not sensible in the sense that if I'm the theta bar type, then B is my least preferred alternative. And I'm only doing this because I think that my vote has absolutely no chance of making a difference. If it had a small chance of making a difference, then instead I should be voting for A or C. So if you put in a requirement that nobody plays a weakly dominated strategy, then that would eliminate these kinds of equilibria. There are also other equilibria. So here's a 2-candidate equilibrium. So let's think of the types who prefer A, vote for A. All the types who prefer B, vote for B. And then there's this third type who actually likes C the best, but all of those types vote for A. Now, why is this an equilibrium? Well, if we're in a world where all the types know that the votes are only going to be cast for A or B, then voting for C is a wasted vote. It's not going to have a consequence in terms of getting C elected, and it leaves the votes then determined between other people's votes for A and B. Therefore, if there is a chance that my vote makes a difference, it's always going to be between A and B. I might as well vote for my most preferred alternative out of those two. And therefore, in this case, the theta bar type has a unique best response in this case to actually vote for A. So this kind of equilibrium actually is referred to as Duverger's law in the political science literature. And it refers to the fact that plurality systems of this type often result in basically only having 2 viable candidates, because you realize that if there's a third candidate who has a low probability of being elected, you're better off casting your vote for one of the 2 candidates who are really in contention, and that focuses all the attention on 2 candidates, and it's really hard for a third candidate to enter and have any chance of winning. That's known as Duverger's law, and you can begin to see it in this type of equilibrium. But basically, plurality rule will have lots of Bayes-Nash equilibria. Okay, so now when we think about the definition we had for direct mechanism, these were ones where people were not reporting their preferences. What they were reporting was an actual vote. But we could think of the direct mechanisms for plurality rule. So instead, let's think of a mechanism where the voters actually are just going to tell you what their type is. So they're telling you their ranking of the 3 candidates, whether they're a theta tilde type, a theta hat type, a theta bar type, etc. Then the mechanism is going to translate those into votes. So theta tilde is as if you're voting for A. Theta hat is as if you're voting for B. Theta bar is as if you're voting for C. So the mechanism takes your announcement of types and then actually translates that into a vote. This is one possible direct mechanism. It could instead be one where saying theta bar translates into a vote for A. So we could change the mechanism. This is one of the possible mechanisms. This particular mechanism is actually going to be manipulable in the sense that if other people are truthful, then the theta bar type would actually prefer to vote for A. So they won't say that they're a theta bar type because that's as if they're voting for C. That's a wasted vote when, remember that there's 49% of the types are of the theta tilde type, 49% are of the theta hat type, and only 2% are of the theta bar type. So they're expecting most of the people to be voting for either A or B. That's going to be a situation where announcing truthfully, if you expected everybody else to be announcing truthfully, wouldn't be a best response, right? They're not going to want to be truthful. They're going to want to say theta tilde because the chances that the decision is really going to come down to one between A and B, and C is really not going to be in the running. So this is just one example of a direct mechanism. In this case, that direct mechanism is manipulable. Okay. Next, what we're going to do is look at other kinds of direct mechanisms and talk in general about the revelation principle, which talks about the relationship between these indirect mechanisms where you're doing votes or maybe sending some complicated message, and ones where instead you just directly report your type and will map an equivalence between any particular general mechanism and revelation mechanism.
This video is going to tell you about the revelation principle, which is one of the core ideas that makes mechanism design possible. So let's begin by finding out what the revelation principle says to us. It says that any social choice function that can be implemented at all by any mechanism can also be implemented by a truthful and direct mechanism. So let's recall what it means for a mechanism to be truthful and direct. We say that a mechanism is direct if it works by having all of the agents simply make a single declaration. You can think of it as writing something down on a piece of paper, giving that to the person who runs the mechanism, and having some decision be made. An indirect mechanism, in contrast, might have a whole sequence of actions and information revelation and subsequent actions that depend on that information revelation, multiple actions by different agents. An indirect mechanism is essentially any sort of imperfect information Bayesian extensive form game. In contrast, a direct mechanism is a simultaneous move Bayesian game. So it's kind of like the sort of Bayesian version of a normal form game. Now, a mechanism is truthful, a direct mechanism is truthful if the equilibrium strategy for every agent is, when they have to write something down on that piece of paper, is just to write down all of their private information. So simply to declare what their type is. So a truthful mechanism gives agents the very easiest strategic problem that they can have. Agents are asked, write me down something on the piece of paper, and the agents say, all right, I'll tell you all of my secrets. I'll just reveal everything to you on the piece of paper, and you go off and make a decision based on that. And what the revelation principle tells us, kind of surprisingly, is that if I can implement a social choice function in any complicated way, I can also implement it in this very simple, truthful, direct way. So let's see how this works. I start with an arbitrary non-truthful mechanism, which indeed may be indirect. So let me draw it here. So what happens is all of the agents have some types because we're in a Bayesian game setting. Then they each take some strategy, which is a function of their types, that tells them how to behave inside this mechanism. And then some complicated thing happens in here. Maybe we have information revelation. There's all kinds of repetitions of agents acting multiple times. And then in the end, eventually something happens. The mechanism decides an outcome. Well, recall that we can look at this whole thing as being a game, right? In the end, this is just a mapping from agents' types and strategies into some outcome that the agents have utility for in the end. And so I can think about an equilibrium of this game. It's just some Bayesian game. And so I can think about these S's all being in equilibrium with each other. And that's exactly what I do when I talk about implementation. If I say that a mechanism implements a social choice function, what I'm saying is that in equilibrium, the mapping from types to outcomes is the same as the mapping that would be chosen by the social choice function. Well, here's the punchline. I want to show that I can make a new direct mechanism which is truthful. And here's how I do it. I take the original mechanism and I kind of embed it in this new mechanism here. So what I do is I say, I'm going to make a new mechanism whose action space is the same as the type space. So I'm going to ask each of the agents, tell me what your type is. And of course, the agents can do whatever they want. They don't necessarily tell me the truth, but they tell me something. And then I take that type that they've declared. So let me, first of all, give a name to that. So I'll call that policy that agent I has for declaring his type to me, his strategy S prime I, which is a function of his true type, right? So he has some way of deciding based on his type how to reveal something to me. So he'll come up with some type, which is a function of the real type that he has, but maybe it's not the truth. Maybe he'll tell me something else. I'll then take whatever he declares to me, and I'll believe him that that's his type, and I'll stick that into S, the strategy profile that we had before, which is our previous equilibrium in the original mechanism. So I'll take that type, I'll then figure out what strategy he would have played in the original mechanism if his type had been what he declares to me, and then I'll simulate the original mechanism. So if it's indirect, inside this new mechanism, I'll kind of run a simulation of the new mechanism. I'll figure out what the original mechanism would have done if everybody had played their declared types under the strategies that were previously in equilibrium, and I'll figure out what the outcome is, and I'll make that the outcome of the new mechanism. Well, I want to claim that this new mechanism is truthful. You can see that it's direct by construction. I want to claim that it's truthful, and this should be kind of easy to see. It's truthful by exactly the same argument that S was in equilibrium. So if this mechanism isn't truthful, that would mean that S wasn't in equilibrium. Why? Because it would mean if this mechanism isn't truthful, then I want to declare some type here that isn't my real type. And if I'm declaring a type that isn't my real type, that means I'm changing the strategy that I would have played in the original mechanism. I would have preferred to also, if I lie to the mechanism here, I would have preferred to lie to myself in the original mechanism so that I would effectively be playing a different strategy than I was playing before. And of course, the whole idea of an equilibrium is that nobody can gain by changing their strategy. So if I wouldn't have wanted to lie to myself in the original mechanism and change my strategy, nor would I want to lie to the mechanism now, because it's already playing a strategy for me that's in equilibrium for the original mechanism. And of course, that being the case, it chooses the same outcomes as the original mechanism. So kind of the slogan for the revelation principle is that the agents don't need to lie in this new mechanism because the mechanism already lies for them, right? We don't actually feed their real types into the original mechanism. Instead, we already apply this strategy of their types just in the way that they were doing before. And given that the mechanism is going to do such a good job of lying for me just in the way that I would have wanted to lie, there's no reason for me to lie again, right? The mechanism is acting kind of as my proxy. The mechanism is doing just what I would like to do, if only I tell it the right thing. And so I should tell it the right thing. That's the idea of the revelation principle. So there's one kind of technical concern to mention here, which is that the set of equilibria is not always the same in the original mechanism and the revelation mechanism. The revelation mechanism, of course, has the original equilibrium we're interested in. That's just what I've shown you. But it could actually introduce new equilibria, which we don't like. It's a bit of a technicality, but it's worth telling you. But let me give you the high-level point here, which is that the revelation principle really is important for mechanism design. So why? What is it good for? Well, there's kind of three ways to see it. it tells us that truthfulness is not a restrictive assumption from the point of view of what can be implemented. Likewise, it shows us that direct mechanisms are not less powerful than indirect mechanisms, which is a bit surprising because it sort of feels like direct mechanisms are much more rich and complicated and they ought to be able to do more. So this tells us, no, truthful and direct mechanisms are enough. If you can show that something is true for truthful and direct mechanisms, you've also shown that it's true for all mechanisms. And that's really important for analysis. So if I want to prove something about the space of all mechanisms, in principle, that might seem really hard to do because I would have to grind through every possible non-truthful indirect mechanism. It seems like a hard set to think about. So what the revelation principle tells me is that if I want to prove that no mechanism exists with certain properties, or that some given mechanism is the best one that exists with certain properties, it's enough to show that it's the best one among the set of truthful and direct mechanisms. And that's a much more manageable thing to do. So really the revelation principle, in telling us that we can restrict ourselves to truthful and direct mechanisms without loss of generality, opens up the analysis of mechanisms. And we're going to see in the future when we prove things about mechanisms, we always begin by saying, without loss of generality, let's restrict ourselves to truthful and direct mechanisms. And that step is very important. That's what makes mechanism design feasible in practice. And so that's why we're telling you about this so early on. This is a really important foundational principle to mechanism design.
Hi folks, it's Matt again. So we're going to look at some examples now of the revelation principle you've just seen. And in particular, let's go back to the plurality rule that we looked at just before in terms of an example. So remember, we have a society of people who are voters. They're trying to make decisions between some set of candidates. So they're trying to make an election here. And in particular, there were three types of individuals: those who liked A, those who liked B, and those who liked C. The C types favored A over B. They're a small part of the population. So remember, that was our example. And we looked at an indirect mechanism, the plurality voting mechanism, where what the actions look like were reports of a candidate. So you just declared which candidate you wanted to vote for, and then the mechanism picked the candidate named by the most agents, or in cases where there was some tie among people getting the most votes, then it would pick randomly among those with a uniform probability. Okay, so that was the plurality mechanism. And now the revelation principle tells us for any equilibrium of that mechanism, there exists an equivalent direct mechanism which will have truthful announcing as an equilibrium. So remember that here there were many Bayes-Nash equilibria. There will be different direct mechanisms for each one of these equilibria in terms of translating the outcomes from the equilibrium in the indirect mechanism into an equilibrium in the direct mechanism. So let's go through that. Remember that we looked at different types of equilibria. Say all voting for A was an equilibrium, all voting for B was an equilibrium. There was the Duverger's type equilibrium where you concentrate on two candidates and you voted for your best candidate out of those two. So the theta tilde voted for A, the theta hat votes for B, the theta bar voted for A. There's going to be many other equilibria. We could have all C equilibria. We could have two candidate equilibria between B and C, A and B. You can get some other kinds of mixed strategy equilibria, but these are more or less the classes of equilibria we can think about for looking at an example of a direct revelation mechanism. So how does that work? Well, now instead of actually casting a vote, what the voter does is just tell us what their preferences are. So they make an announcement that they're one of these three types. Now, if we want to think about the indirect mechanism, which was the plurality rule equilibrium, where all people vote for A, so we think of the mechanism plus what the equilibrium was. Okay, so we can think about one of the equilibria for the plurality rule equilibrium where everybody was voting for A. So what's the direct mechanism for that? Well, now each person states their type. Now remember, in the indirect mechanism, everybody was voting for A. So what happens in the direct mechanism is the direct mechanism translates every type announcement into the equivalent of the vote for A and the outcome is just now going to be A, independently of what people's types are announced. So it's as if everybody voted for A, and then the outcome is just A. Now, truth is in equilibrium, right? So I have, no matter what I do, it's as if I'm voting for A. I might as well say my true type. So this would be the direct mechanism associated with that indirect mechanism and equilibrium. Now, if we changed it to the equilibrium where people are voting either for A or B, depending on which was their favorite, then again, the direct mechanism is going to have people announcing their types. And then what happens is the mechanism is going to translate that into what they would have done. So it's saying theta tilde is as if you're voting for A, theta hat is as if you're voting for B, theta bar is as if you're voting for A, and then it'll count up how many theta tildes it gets, how many theta hats it gets, how many theta bars it gets, and if the majority of votes was for B, it'll end up being a B. If it was for A, it picks an A. And now, again, since that was an equilibrium in the indirect mechanism, this is an equilibrium of the direct mechanism. Now we see that taking that same mechanism that we started with, we have a different direct mechanism for each equilibrium that we had in the indirect mechanism in order to make sure that things are incentive compatible. Okay, so that takes us through the direct revelation mechanisms. These are going to be very useful for proving theorems because any equilibrium that we can work with an indirect mechanism, we always know that there exists an equivalent direct mechanism. That's going to make our life a lot easier because it means that whatever we can do with indirect mechanisms, we can also do with direct mechanisms. And so we can just concentrate on working with those and making sure that we're getting all the possible outcomes that we could have gotten with the indirect mechanisms.